Okay, so right, so I assigned homework 17. So please, if you have questions, say it out loud, like that student just did. I think it was Daniel. Say it out loud. I can't see what's in the chat. There's too many things going on at once on my screen to see what people are writing in the chat. Okay. Okay, so are there any questions about homework 17? Any questions at all? Keep in mind the exam is next Monday, right? This coming Monday. Okay, so there's no questions. Okay, so I'm going to start with the material. Okay, so let's continue then. So new share. Okay, so there's no questions about homework number 17. Let's go to the lesson. Okay. So last class I was talking about 8.1, right, which is on sequences. So we define sequences, right? And so we also saw them as functions, right? So we saw them as functions from the set of positive integers to an arbitrary set, right? And so we also talked about limits. And we talked about the limit of a sequence, right? So what does it mean to have a limit of a sequence? I'm going to write a limit of a sequence, okay? So we talked about a limit of a sequence and what that means, right? And so we had two definitions of that. Okay, so that's some of what we did last class, okay? So then we also talked about what it means to have a sequence that diverges to infinity, right? So if the limit of a sequence is infinity, what does that mean? Okay, so that was last class. And so this class we're going to continue. Talking about sequences. Okay, and then depending how quickly we go, hopefully we can also talk about series. Okay, so if there's time, we will also talk about series. Okay. Okay, so let's begin. So I ended last class with the definition of a sequence that diverges to infinity. And so I'm going to continue after that. And so after that are the limit laws for sequences. Okay, so now that we have the definition of a limit, we can talk about the laws, limit laws. Okay. So if A sub n and B sub n are convergent sequences, and C is a constant, then we have the following laws. Okay, so I'm going to enumerate them. So the limit as n approaches infinity of A sub n plus B sub n is equal to the limit as n approaches infinity of, we'll copy this okay, as n approaches infinity of a sub n plus limit as n approaches infinity of b sub n. Okay, so that is the first limit law, that the limit of a sum of sequences is the sum of their limits. The second law is that if you take the limit of the difference of two sequences, and what you think happens does happen, that it's the difference of their limits. So that equals the limit of a sub n minus the limit of b sub n. So that's the second limit law. The third limit law is if you take the limit of a constant times a sequence, of a constant times a sequence, that's equal to a constant times the limit of that sequence. Okay, so that's the third limit law. You can move the constant out of the limit. Okay, another law, which I'm going to group it with the third one because it involves a constant, is that the limit of a constant is equal to that constant. Okay, so there's also the limit of a constant is a constant. So these are two equations in 3 that involve a constant. 4, if you take the limit of a sub n b sub n, it's equal to the limit of a sub n times the limit of b sub n if both limits exist. Oh, well, okay, sorry. We already have that. We have that up here. Okay, if a sub n and b sub n are convergent sequences, and that means their limits exist, and c is a constant, then these things happen. Okay, so we already have that these two limits exist. You can calculate them and get finite numbers. Right? If either of these limits is infinity, that would mean it's not a convergent sequence, that both their limits do not exist. Okay, so this only applies where both of these things are numbers that you could multiply to get this limit. Okay, 5. If you take the limit, you take the limit of the fraction a sub n over b sub n, that's equal to the fraction where the numerator is the limit of a sub n, and the denominator is the limit of b sub n. Now, both these limits have to exist already from this assumption. This assumption applies to all of them. And so both of these are numbers, right? Both these limits in the numerator and denominator are values or numbers. And so you get this limit is this number divided by this one. But just like any fraction, the denominator can't be 0. And so this is if the limit in the denominator, the limit b sub n, does not equal 0. Okay. Okay, and so the reason for that is only that the denominator can't be 0. It has nothing to do with properties of a limit. Right, and then 6, if you take the limit of a sub n raised to the p power, this is equal to the limit of a sub n raised to the p power. Okay, and this is if p is if p is positive, and a sub n is positive. Okay, so if every term a sub n is positive, if p is positive, then the limit of each of the a sub n's raised to the p power, all these p powers, the limit of these p powers is the limit raised to the p power. Okay, but you need p positive and every term a sub n in the sequence positive. That's what this stands for. Okay, this inequality here doesn't mean a particular term is positive. It means every term of the sequence is positive. Okay, so these are 6 limit laws where 3 has technically 2 equations. So there's 7 equations in these 6 laws, and those make up the limit laws for sequences. Okay, so this is important, and so I'm going to put this line here just to separate this from everything else. Okay, so this is an independent idea that I think is important to look at and think about. So between these lines are the limit laws for sequences. Okay, so let's keep going. So we have those limit laws. So the squeeze theorem can be adapted for sequences. Okay, so that's as follows. And so, okay, and so this is called the squeeze theorem. For sequences. Okay, so the squeeze theorem for sequences, and so it goes like this: if every term a sub n is less than or equal to each corresponding term b sub n, which is less than or equal to each corresponding term c sub n, and this is for n greater than or equal to n naught for some n naught, and the limit of a sub n is equal to the limit of c sub n, at which is equal to some real number L, then what you get is that the limit of b sub n is equal to that same real number L. Okay, so this is called the squeeze theorem for sequences. And so I'm just going to, I thought I wanted this way, but now I realize I don't. Let me put the formatting back the way I had it. Okay, and I'm just going to put this like here. Okay, that's the conclusion. Okay, so the squeeze theorem for sequences. If you have 3 sequences, AN, BN, and CN, and the terms B sub n are sandwiched between terms AN and CN for every sufficiently large n. So there's some point in the sequence, let's say the 20th term. We're starting at the 20th term, and every term afterwards, the nth term is less or equal to the nth term of sequence A is less or equal to the nth term of sequence B, less than or equal to the nth term of sequence C. And this is for every n starting at some n naught. Okay, so this would be the starting point. Okay, so there's some starting point where all the sequences line up in this way. Okay, it doesn't have to be from the beginning. So these inequalities could fail in the first 30 terms, but then starting with the 31st term, you do have them line up like this. That's fine for this theorem. Okay, so if that happens and the limit of the A sequence is the same as the limit of the C sequence is L, then the limit of the in-between one is also L. Okay, so we're looking at the long-term behavior of these sequences. We want to know how going far out, if A sub n is approaching one thing and Cn is approaching one thing, then the thing in the middle has to approach that same thing. Okay? And since we're looking far out, we don't care about what happens early in the sequence. It makes no difference. And so we only need this relationship for a sufficiently large n. Okay, and it's for all n growing equal to some value n naught. Okay. And so it happens in the first n naught minus 1 terms. It makes no difference when it comes to the limiting behavior of all these sequences. Okay, so that's the squeeze theorem for sequences. Okay, if you right, so if you want to visualize that, then let's say you had a sequence A sub n, which I'm going to label as blue. So let's say you had a sequence A sub n whose terms, look like this, right? And so you can see how going far out it's approaching 0, right? Let's say you had terms B sub n, that look like this. Oh wait, I'm gonna just line them up so they're vertically in the same. They have the same x coordinates. Okay, so then let's say for the red sequence, you have something like this. Okay, so here's your red sequence, and then you have the in-between green sequence. Okay, so then let's say you have this sequence green here. That green is very close to the line, closer than B is. Okay, so let's say you have these three sequences, right? So the red is the A sub n. So you have three sequences here. You have this one, you have a middle one, and you have the last one. The blue one is the largest one. I mean, that's Cn. That's Cn. And then in the middle, you have the green sequence, B sub n, right? So you see how starting with this term, starting from here, well, actually a blue, green, okay, that doesn't match up. Starting from here, start from here and going right. These three terms all have this order, right? It goes red at the bottom, green in the middle, blue at the top. Red at the bottom, green in the middle, blue at the top. Red, blue, green, red, blue, green, red, blue, green, right? And see, before that, you don't have this pattern. So in the first three terms, they don't line up this way. But starting with so this is the first term, second, third term, third. This is 1, 2, 3, 4, 5, and so forth, right? So starting with the fourth term, the sequences line up. So this would be for every n greater than or equal to 4. See that? So for all the terms starting with the fourth term, these three sequences line up in this way. And now the limit of A sub n is equal to 0. The limit of the reds are 0. The limit of the C's, not the B's, the C's, the limit of the C's are also 0, right? So the blues are also the blues are tending to 0 and the reds are tending to 0, and green is sandwiched in between them, squeezed in between. The values are squeezed in between, starting at n equals 4. So for every n greater to 4, green is in the middle. The conclusion with all this is therefore the limit of B sub n is 0. That's the conclusion. That makes sense? That's what the squeeze theorem for sequences is saying. Okay, so the green sequence is approaching 0. You can't hear me anymore? Can you hear me now? The volume's on. The volume's on, right? So you should be able to hear me. Can anyone hear me? Can someone hear me? Okay, so it might be your audio. Okay, I'll try talking loud enough. It might be on your end though. Okay, so we have the squeeze theorem for sequences. So next, let's do another theorem. Okay, so theorem, if the limit as n, if the limit as n approaches infinity of the absolute value of A sub n is equal to 0, then the limit as n approaches infinity of A sub n is equal to 0. Okay, so if the limit of the absolute value of the terms is 0, then the limit of A sub n is 0. Okay. Okay. So, or maybe someone else. Okay. So, this just means that if the distance, the values of the sequence away from 0 are is tending to 0, then it would have to go to 0. Okay. So hopefully that's intuitively obvious. Okay. So example 10. Find the limit of n over n plus 1. Okay, so we want to find the limit of n over n plus 1 solution. Okay, so step 1. So I'm going to split this up into steps. Step 1, divide the numerator and denominator by the highest power of n that occurs in the denominator. Okay. Step 1 is divide the numerator and denominator by the highest power of n that occurs in the denominator. And
Professor,
step 2, yeah.
you doing example 10 or example 4?
Example 10. Yeah. Oh no, it's just example. Sorry. Okay. It's example. Okay. It might be example 4 in the book. Okay, so I wrote example. Okay. The LE looked like a 10. Okay, so example, find that limit. Step 2, use limit laws to finish the problem. Okay, so let's do it. Okay, so first we take our original limit, the limit of n over n plus 1, and this is equal to, so we're still taking the limit when we divide. So we have in the numerator, we divide the numerator by n, and we divide the denominator by n, because the highest power of n in the denominator is n. That this n here that I highlighted is the highest power of n that occurs in the denominator. Okay, I'm going to underline that part. So make sure to point that out to yourself. The highest power of n that occurs in the denominator, right? That's the thing you're dividing the numerator and denominator by. So since it's n over n divided by n plus 1 over n. And now that's equal to the limit of, well, the numerator is 1, and the denominator now, n plus 1 over n is 1 plus 1 over n. Right? So now we have that. Well, according to the limit laws, so we have the limit. So write this down, right? Make sure you have this, at least this expression, better everything, but at least this have written down, okay? We want to calculate this limit. Now, if you look at the limit laws, the limit of a fraction is the limit of the numerator over the limit of the denominator, right? So you want to calculate the limit of 1 over 1 plus 1 over n, okay? Sorry, the battery is running low again. Quickly plug this in. Okay. Hold on 1 second. Okay, good. Okay, so you want to find the limit of 1 over 1 plus 1 over n, right? What that is. Okay, so the limit of 1 over 1 plus 1 over n, first look at 5. It's the limit of 1 over the limit of 1 plus 1 over n. The limit of 1 is the limit of a constant 1, which is 1. So the numerator becomes 1, and that's from property 3. So you see how the numerator is 1. I'm not writing every step, right? So I guess I'll write every step. This is equal to the limit of 1 over the limit of 1 plus 1 over n. Okay? Right? And so this is applying this limit law here by limit law 5. So I'm going to put by 5. And these numbers are referring to the laws just above, okay? Now this is equal to the fraction 1 divided by the same denominator, right? Okay. The limit of 1 plus 1 over n. And this is by 3, right? The limit of a constant, this one, is that constant, okay? Okay, so that's by 3. And then this is equal to, so now we have this thing. And so keep in mind that over here, this is if the limit of the denominator is non-zero, right? If you have the limit of that thing is non-zero. So if the limit of 1 plus 1 over n is not equal to 0, right? That's a condition for, also both limits have to exist, right? Okay, so this is equal to 1 over this by 3. Now what's the limit of that? It's the limit of a sum.
Professor,
Yeah,
can you explain the by 3 one?
sure, this one?
Yeah.
I'm saying that the limit of 1 is equal to 1.
Oh, that's all?
Yeah, because 3 says the limit of c, which is a constant. 1 is a constant, so the limit of 1 is 1. Make sense?
Oh, okay, yeah.
Right? If every term of your sequence is 1, then the limit of those terms is that same 1. Okay? That means that the values of the sequence get as close to 1 as you want as you go out. Since it's always 1, it's actually 0 away from 1. It's always 0 away from 1. And the definition of limit says that your terms, in a sense, tend towards a certain value. They're tending towards 1 because they're always 1. Okay. Now, the denominator is the limit of 1 plus the limit of 1 over n. Okay. Keep in mind that when you calculate these limits, you could normally just go straight to the answer without writing all this. But most students don't know all this justification and maybe don't appreciate it. It's good to appreciate and understand these laws and how they're being calculated. Okay, it's all from these 6 laws above. So here, this is law 1. The limit of a sum is the sum of their limits. That's 1. And so we're applying 1 here. So this is by 1. And so now this is equal to the fraction 1 over 1 plus the limit of 1 over n. And so this is again, well, so this is by 3, right? Because 3 says the limit of a constant is that constant. And so the limit of 1 is again 1, right? Just like the limit of 1 was 1. So we're doing the same thing here. Now, we're almost done. And so you just have to use the fact that so we have 1 over 1 plus 1. And this is by the fact that the limit of 1 over n, that's equal to 0. This is by the fact that this limit is 0. And so when you calculate this limit, you get 0, and you plug that in there. And so then this is just equal to 1 by algebra, right? By basic algebra. I'm not saying basic algebra to say you're dumb if you don't know it. I'm saying that just so you don't think it's something more complicated, right? That this is equal to 1. Now forget all this weird stuff happening. 1 over 1 plus 1 is 1, right? That's all that's happening in this last equal sign. Okay, so this is all saying, so the conclusion here, the conclusion is that the limit of n divided by n plus 1 is equal to 1. That's the conclusion. And so we're done. The problem was find the limit. We've done it. It's equal to 1, right? We divided the numerator and denominator by the highest power of n that occurs in the denominator to express this limit as this limit. And then from here, we did step 2, which was to use the limit laws to calculate this limit. Using the limit laws, we got that this thing was equal to 1 by applying law 5, then law 3, then law 1, then law 3 again, and knowing that this limit is 0. Okay, so that's how I use the 2 steps there. So when you have a calculate limit problem, oftentimes you can break it down to these 2 steps. Sorry. We have a polynomial here, right? We have a polynomial divided by a polynomial. That's why I use these 2 steps. Okay, so these 2 steps apply for finding the limit of a polynomial divided by a polynomial. Okay, so when you have a polynomial divided by a polynomial and you want the limit of that, that's when you use these 2 steps. Okay, so it's something different, you wouldn't use these 2 steps. So another example is calculate the limit of ln of n divided by n. Okay, so solution. So if you take the limit of ln of n over n, this is equal to, now I'm going to apply here L'Hopital's rule. Okay, the much feared L'Hopital's rule. So L'Hopital's rule, right, with the conclusion of the theorem, right, without the justification, just looking at the conclusion, the limit of this is equal to the limit of the derivative of the numerator, which is 1 over n, divided by the limit of the derivative, divided by the derivative of the denominator, which is 1 with respect to n, right? So this is by L'Hopital's rule. Okay, so by L'Hopital's rule, this limit equals that one. Okay, so then before I justify it, I just want to show how it's immediate after that. This is now the limit of 1 over n, right? Now we have the limit of 1 over n, and that's equal to still 0. Okay. Okay, and so now we have that. Okay, now looking at L'Hopital's rule, okay, so looking at L'Hopital's rule, we have that the okay, wait, let me make a point here. If you take this limit, it's the same as the limit as x approaches infinity of ln of x divided by x, right? And so then this is the same as the limit as x approaches infinity of 1 over x, which is now this, which is 0. Okay. So here, these are terms of a sequence. Here, these are values of a function. Okay. So we had a previous theorem, right, that said that if you had a function that whose limit was 0, if who had a limit, a function whose values had a limit, and the terms of a sequence are values on that function. If your function has a limit going somewhere, then the terms of your sequence have that same limit. And so here, these are terms of a sequence whose values lie on this graph. And now here, this is a continuous function that we're taking the limit of. And so now that we have a continuous function, we can apply L'Hopital's rule here. And so then we're going to get L'Hopital's rule involves using continuous functions, right? And so with derivatives, and so we're not going to, we start thinking of values of sequences, then we switch over to values of functions, such that the terms of these sequences are values on these continuous functions. Okay. Okay. To illustrate that, it would be like saying, instead of, if you had a function like this, instead of taking the terms of a sequence which had these heights, right? Instead of thinking the values of a sequence as heights like this, you could think of them as points lying on a function. And so by looking at what this function is doing, we're correspondingly realizing what's happening to the sequence that has the values on that function. Okay, so that's what's happening from here to here. And then L'Hopital's rule says you take the derivative numerator and denominator, and that limit. Okay, so there's 4 things to check, right, for L'Hopital's rule. Right, so the numerator and denominator function are differentiable. So that's good, right? The derivative of the denominator, which is g prime of x, right? G prime of x is the derivative of the denominator. The derivative of the denominator is non-zero for x sufficiently large, or x near infinity. Okay, so when you take x sufficiently large for this limit, right, the derivative of the denominator is 1 here, right? So, and so note that f of x is the original ln of x in the numerator, and g of x is the function that's over x, right? Okay, so the denominator is non-zero. That's good. Okay. Another one says that the limit on the right side exists. So this limit, the limit on the right, limit of f prime of x over g prime of x, which is equal to the limit of, well, f prime of x is 1 over x divided by 1, right? So we have this, right? That limit exists, it's 0, right? So this limit, so the limit exists, right? And so that's good. And so we have the limit exists on the right side. We have that the numerator and denominator are differentiable. The denominator is non-zero for x near infinity or x sufficiently large. And we also have one that says that, so numerator and denominator are differentiable. Then you have that the oh, right. And then the original limit, which in this problem is the limit of ln of x over x, is of indeterminate form. In this case, okay, this is x. Is of indeterminate form. The limit of the numerator is infinity, and the limit of the denominator And the limit denominator is also infinity. So it's of indeterminate form, infinity. It could also be 0 over 0, but in this case, it's infinity over infinity. That's good. So all four things check out. And so we can use L'Hopital's rule, which says that the limit of this equals the limit of that. Okay, and then that limit is 0. And so the original limit is also 0. And so we are not done that problem. Okay, next one. Next example. Determine whether the sequence a sub n, which is equal to -1 to the n, is convergent or divergent. Okay, so solution. So the solution is, first let me say the answer. The intuitive answer. Okay, so a sub n is just the sequence that alternates between 1 and -1, right? So if the sequence is alternating between 1 and -1, it can't possibly have a limit. Okay, so if, let's say, here's your x-axis, here's your y-axis, and your sequence a sub n starting at n equals 1. The sequence a sub n is defined by -1 to the n. So n equals 1. This is 1. This is -1. At n equals 1, it has value 1, right? N equals 2 would be 1, and so you'd alternate. Oh, okay, so these are the. And it keeps going. And so it's just going to alternate in values, right? These are the terms of your sequence a sub n. So a sub n at n equals 1, a sub 1 is equal to -1. A sub 2 is equal to -1 squared, which is 1. A sub 3 is -1 cubed, which is -1. This is 1, 2, 3, and so forth, right? So this is 1, 2, 3, 4, 5, 6, and so forth, right? And so these are the values of the sequence for those numbers, right? So it's going up and down, right? So this sequence cannot have a limit. A limit would be saying that all the terms sufficiently large are getting arbitrarily close to some real number, right? But if I chose 1 as the limit, right? If I chose 1 as the limit, then sure, the even terms would all be 1. All the even terms would be 0 away, so they'd be sufficiently close. Every odd term would then be 2 away. And so I can't say all the terms after some points are arbitrarily close to that number 1. Let's say I started at 4, right? If I started at 4 and went and kept going right, the argument would fail that all the terms starting with 4 would be arbitrarily, the terms would be, sufficiently close to 1, let's say 1/2, right? You'd have 2 terms that were 2 away. If I wanted to go within a millionth of 1, all the odd terms would still be 2 away, right? It wouldn't matter how far out in the sequence I would go. There'd always be a term 2 away from 1, right? And so I couldn't say that all the terms after some starting point would be within a millionth of 1, okay? So 1 is not the limit, right? 1 is not the limit. So it's the reason I chose red to put there. So 1 fails as the limit, right? Now, -1 also fails for the exact same reason, right? There's always a value of 1 at some point for every even term. And so you can't go sufficiently far out into the sequence and say all the terms after starting here, from here, are within 1/2 of -1. Because you always have a term at 1, you always have a term 2 away from -1. And so -1 also can't be the limit. And any other value other than -1 or 1 also can't be the limit, because obviously the terms would fluctuate from 1 and -1. And even if I chose, even if I chose the limit really close to, let's say, 1, I could just take the distance to be half of that and say, okay, none of the terms will ever get within a millionth of, of this limit, right? So they can't all be within a millionth of that value, right? Okay, so there is no limit for this sequence. So first, let me say the intuitive answer. There is no limit. So the sequence diverges, right? That's what a sequence diverging means. The sequence has no limit, or it has infinity as a limit, okay? Plus or minus infinity, right? A sequence diverging. So as a reminder, a sequence diverging means it does not have a finite limit. Okay, infinite limits are from result in diverging sequences. Okay? So we can't have an infinite limit, and we need a finite limit, but it doesn't have it, so it's divergence. Okay, so that's the intuitive answer. Now to explain mathematically why that limit can't exist, let's say you take the limit of the absolute value of -1 to the n over n. Oh, wait, sorry. Okay, that was okay. So I gave this explanation, right? If a sub n, here's something. Okay, if a sub n is convergent, then every term a sub n such that n is greater or equal to n naught for some n naught is within epsilon positive of some number capital L. So if a sub n is convergent, it has a limit. And that means, by definition of limit, that every term a sub n, for every n greater or equal to some n naught, is within epsilon positive of some number L. Okay? But there are always terms of 1 and -1 further out into the sequence, regardless of where we start. That means that there are always later terms that are 2 away from each other. So we cannot choose, we cannot find, so it is impossible to find a real number such that all the terms a sub n are within any epsilon positive of that real number for a sufficiently large n. Okay, so the sequence diverges. Okay, so that's the explanation of that. Okay, another example. Evaluates the limit as n approaches infinity of -1 to the n divided by n, if it exists. Okay, so solution. Okay, so solution.
Wait, Professor, can you go up a little bit while you're working on it?
Here?
Yeah, that's good. Thank you.
Okay, you're welcome. I could go further up without stopping. Okay, so if you take the limit of -1 to the n divided by n, right? If you want to know what the limit of the absolute value that is, well, then the -1 goes away, right? because -1 to the
You
n
could go
for
back
any
down.
n. Sorry?
You could go back down. Thank you.
Okay, all right. Now I just will when I need to, because I haven't yet. Okay, so now this is the limit of 1 over n, because n is positive, so the absolute value of n is itself, and the absolute value of -1 to any n is 1. So now it's the limit of 1 over n, which is 0. So what we showed is that the limit of the absolute value of the terms is 0. But therefore, by theorem, right, an earlier theorem says the limit of the absolute value of the terms is 0, and the limit of the original sequence is 0. So therefore, by theorem, the limit of the sequence we want, the limit of the sequence we care about, -1 to the n over n, is also 0. Okay, so if the limit of the absolute value of the terms of the sequence is 0, then the limit of the terms of the original sequence is 0. And so that's what happens here. And so the result is very fast. Okay, and so as a reminder of what that theorem said, remember, if the limit of the absolute value of the terms of your sequence is 0, then the limit of a sub n is 0, right? So we're using that fact where the a sub n here is -1 to the n over n. Okay. Okay, so in that problem, it boiled down to finding the limit of the absolute value of the terms. Okay, so next is the continuity and convergence theorem. Okay, if the limit of a sub n is equal to L, and the function f is continuous at L, then the limit of f of a sub n is equal to f of L. Okay, so this is called the continuity and convergence theorem. If the limit of a sub n is L and the function f is continuous at L, then the limit as n approaches infinity of a sub n is equal to f of L. Okay, and so the best way to illustrate that is with this example. Find the limit as sine of pi over n. Okay, so we want to find the limit of sine of pi over n. And so the solution is to use the continuity and convergence theorem right above it there. Okay, so the goal is to use the continuity and convergence theorem to find this limit. Okay, so observation, right? Sine of pi over n is continuous. Sine of that. Observation, sine of x is equal, sine of x is continuous everywhere, right? The function sine, if you draw the graph of sine, you can draw without lifting your hands, right? That's illustrating how sine of x is continuous everywhere. Thus, sine of x is continuous specifically at x equals 0. Okay, so sine of x is continuous specifically at x equals 0. That's what we need. We have it's continuous everywhere, but what we need for this theorem is it's continuous at 0. Right? So the limit as a sub n, we'll put the limit of So the limit of pi over n is 0, right? And so here, note that notation is that we're going to let a sub n equal to pi over n. Okay, so a sub n here is pi over n. This is pi over n, right? And so that means that the limit of sine of pi over n is equal to the limit of sine of a sub n. Okay, so here the limit of sine of pi over n, which is what we want, is the limit of sine of a sub n, where a sub n is pi over n, right? And also let f of x equal sine of x. Okay. So the limit as n approaches infinity of a sub n is 0. Okay. So here, this means L is 0 for this problem, right? The limit of a sub n is 0, and you also need that the function f is continuous at 0. So f, which is sine of x, so that means, right? So f, so the function f we defined is continuous at 0, at L equals 0. Okay, so the limit of these terms is 0, and the function f of x equals sine x is continuous at 0. And so the conclusion of the continuity and convergence theorem says, since we showed all the conditions hold here, the conclusion of the continuity convergence theorem says that the limit, right, the limit of f of a sub n it says that the limit of f of a sub n, limit of f of a sub n is equal to f of L. So this is equal to the limit of f of a sub n, which is sine of pi over n, because a sub n is pi over n, and sine of a sub n is sine of pi over n. So the limit of f of a sub n, which is that, is equal to f of L, right? F of x is sine x, and so f of 0, L is 0, so f of 0 is sine of 0. And so this limit is equal to sine of 0. Sine of 0 is 0. And so that's the answer. So the answer is 0. Okay, so we have an observation here, right, that sine x is continuous everywhere. Thus, sine of x is continuous. Thus, sine of x is continuous specifically at x equals 0. We have this notation, right? Okay, and so then, and so that means that that equals that. We also have this. Okay, and so the function f is continuous at L equals 0. Okay, so make this look nice. And then, and so then the conclusion is that. Okay. Okay, so it could be weird. It could be hard to keep track of everything that's going on in that theorem, right? Okay. Okay, so a shorter way to explain this, which I think is less illustrating of what's going on, but you can write this. The limit of sine of pi over n is equal to sine of the limit of pi over n. And what that's equal to sine of 0, which is 0. Okay, right? But there's reasons why. The reason we can move the limit outside of sine to inside of sine, right, is because the limit of the pi over n's is 0, and sine is continuous at 0. Okay, so okay, and so this is because the limit is 0. This is because the limit of pi over n is 0. And sine is continuous at 0. Okay, so because the limit of this thing, you're taking the limit of sine of pi over n. So since the limit of pi over n is 0, and sine is continuous at 0, you can move the limit inside. And so once you move the limit inside, then the limit of that is 0. Sine of 0 is 0. Okay, that's the shorter way to explain it. Okay, example. Another example. Discuss the convergence of the sequence a sub n. A sub n is equal to n factorial divided by n to the n power, where n factorial is equal to 1 times 2 times 3 times ... times n. Okay, solution. Okay, so we want to find we discussed the convergence of this sequence. So there's a converge, there's a diverge. And to what if it converges? Okay, so a sub n is now equal to, so let's point out that if you have n factorial here, it starts at 1 and goes to n in the numerator, right? So what we have here is n factorial. So we have 1 times 2 times 3 times ... times n, right, in the numerator. And the denominator, we have n times n times n times ... times n, where there's n of them. Right? So you can break this up. You have 1 over n from the 1 and the n there, and then the rest of it. For the rest of it, you have this fraction here, which is multiplying from 2 to n. And the denominator, you just have 1 less many n's that you're multiplying, right? Okay, so now you have n minus 1 many n's in that fraction. Okay, now when you keep going, okay, so notice that this fraction, you have 1 over n here, and then you have a product of, you have a fraction here where every term here is less than or equal to this corresponding term here, right? It's strictly is less than or equal to, where the first term, 2, is strictly less than n, right? So this fraction here, inside here, is less than or equal to 1, right? So this fraction is less than or equal to 1. And that implies that that first you have 0. First you have 0 is less than or equal to a sub n, because these terms are all non-negative. But then you also have now, because of this, your a sub n is 1 over n times something at most 1. And so each a sub n term is at most 1 over n. Right? Each term a sub n is 1 over n times a fraction that's at most 1. And so that means the largest a sub n could be is 1 over n. Right? And it's not negative. So it has to be between 0 and 1 over n inclusive, meaning it can include 0 and that. Okay, so, but maybe not. Okay, we're just going to include them. So, and so also note that the limit of zero
Professor?
is 0. Yeah.
For the solution for the sequence for n is less than or equal to 1. Wait, oh no, it's not for n is less than or equal to 1. It's for while the whole expression is less than or equal to 1.
This part of
Right.
it, what's in the parentheses, is less or equal to 1.
Yeah.
You see it?
Yeah.
Okay, so this thing is less or equal to 1. And so this is at most 1. So a sub n is 1 over n times something at most 1. And they're all both non-negative. So a sub n is at most 1 over n. And okay, so now a sub n is sandwiched between those two things. The limit of 0 is 0, and the limit of 1 over n is 0. And so by the squeeze theorem for sequences, the limit of the in-between terms, the limit of the a sub n's is 0. And you're done. And so now we found the limit of a sub n, 0. So to discuss the convergence of the sequence converges to 0. Which I said here, but in words I just wrote it again just so it's clear. So that's another example. Now, the next example. For what values of R is the sequence R to the n convergent? Okay, so for what values of R is the sequence R to the n convergent? So R is a real number, right? So note R is a real number. Okay, so for what values of R is that sequence convergent? So first note that if you take the limit of R to the n, right, it's going to equal okay, so it's going to equal infinity if R is greater than 1, right? If R is greater than 1, like 5, then as the powers get larger and larger, 5 to the n is going to get arbitrarily large, right? So that's infinity if R is greater than 1. It's 0 if 0 is less than R, less than 1. Okay. Okay, so if R is a fraction, let's say like 1/2, raising 1/2 to larger and larger powers would make it smaller and smaller and tend to 0. So the limit of R to the n is 0 if R is strictly between 0 and 1. Now, if you take the limit of one to the n, well, the limit of 1 to the n is just 1, right? Because the powers, you could say that if you want, the technical reason is you could take the limit of 1 and raise it to the nth power, right? That equals that. But the limit of 1 is 1. So this is so this is equal to this is just equal to 1. Which is 1. This is just 1, right? Because then it's a sequence of ones, and so its limit is 1. I'll just think. Okay, and the limit of 0 to the n is 0. Same reason, all the terms of the sequence 0 to the n is 0. So the limit of a sequence of zeros is 0. So we have now for r greater than 1, r between 0 and 1, r equal 1, and r equals 0. And so what's left is when r is negative. So if negative 1 is less than r, less than 0, then 0 is less than the absolute value of r, which is less than 1. And so the limit of the absolute value of r to the n is equal to, well, we said earlier that the limit when the terms are between 0 and 1 is 0, right? So this is equal to the limit of the absolute value of r raised to the n, just putting in this in between step, right? Absolute value of r to the n is absolute value of r to the n. These terms with absolute value of r is strictly between 0 and 1. And so the limit is going to 0. That's 0. Okay. Now, if the limit of the absolute value of r to the n is 0, then the limit of your original sequence is 0. Okay. And so that means for these values of r, the limit of r to the n is 0. And so, and then if r is less or equal to negative 1, then, right, then the limit of r to the n does not exist. It's also worded as DNE, does not exist, right? So the sequence diverges, right? And why does it not exist? Because if r is less or equal to negative 1, when you take larger and larger powers, when n is even, when you raise a negative number to an even power, it's positive. When you raise it to a negative power, to an odd power, it's negative, right? So the values of r to the n for r less or equal to negative 1 are just going to alternate between positive and negative. And since r is less or equal to negative 1, if let's say r was negative 5, right? So if r is negative 5, then the base is if the base was negative 5. So as the powers get larger and larger, the absolute value is getting bigger. And it's just getting bigger, positive and negatively, right? So it's alternating in values, and it's getting further and further from the x-axis, and it's jumping up and down from positive above to below. And so there's definitely no limit for that sequence. Okay, and if r equals negative 1, like I was saying, then you're just alternating between positive and negative 1, which we showed has no limits. Okay, and so for each case, I showed, what happens. And so the conclusion, putting all that together, the conclusion is that the limit as n approaches infinity of r to the n is equal to, so putting these cases together that I wrote down, it's equal to infinity if r is greater than 1. It's equal to 0 if 0 is less than r less than 1. It's equal to 1 if r equals 1. It's equal to 0 if r equals 0. It's equal to 0 if negative 1 is less than r less than 0. And it's diverges if r is less or equal to negative 1. Okay, so I repeated some values, but so you can put them together, right? But I just put each of them in a separate row here. So you can see, okay? And remember, this means it diverges here also, right? The limit of infinity means you have a divergent, right? Diverges here. Right? Okay, so diverges here because it's infinity, and then it converges here, well, these places, 0 or 1. Okay, so it only converges to a non-zero value at r equals 1. Otherwise, if it converges to 0 in certain places, or then it diverges. Okay, here I just say diverges because it's not even, it's not, you can't say positive or negative infinity. So you just say it diverges. Okay, it doesn't have a limit. Okay, so that's the solution to that problem. Let's keep going. Definition. A sequence, A sub n, is called increasing if A sub n is strictly less than A sub n plus 1 for all n greater or equal to 1. So a sequence A sub n is called increasing if A sub n is less than, strictly less than A sub n plus 1 for all n greater or equal to 1. Okay. So that is A sub 1 is strictly less than A sub 2, strictly less than A sub 3, strictly less than A sub 4, strictly less than that. Keeps going. Okay. It's a period there. I'm going to leave the period out so it doesn't do that. It is called decreasing if A sub n is strictly greater than A sub n plus 1 for all n equal to 1. Okay. That is A sub 1 is strictly greater than A sub 2, strictly greater than A sub 3, strictly greater than A sub 4, strictly greater than dot, dot, dot. Okay. A sequence is monotonic if it is either increasing or decreasing. So also when I talked about decreasing, right, I use a greater than sign, which might be weird, but it's saying this: if A sub 1 is greater than A sub 2, then that means that the value of A sub 2 is smaller than A sub 1, right? That means as you go further onto the sequence, your terms are getting smaller. So a sequence decreasing means A sub 1 greater than A sub 2, greater than A sub 3, greater than A sub 4. And so what confuses students sometimes is that you're defining a decreasing sequence with the greater than symbol, kind of, and you're using the less than symbol for increasing, right? But if A1 is less than A2, that means that the value of the sequence got larger from the first to second term. And so in order to increase, for a sequence to increase, the previous term has to be less than the next term. Okay. In order for a sequence to decrease, the previous term has to be more than the next term. Okay. Right. And a sequence is monotonic if it is either increasing or decreasing. Okay. So that's the definition there of an increasing sequence, a decreasing sequence, and a monotonic sequence. Okay. Example. The sequence (3 over n plus 5) is decreasing because for any n greater or equal to 1, you have that 3 over n plus 5 is strictly greater than 3 divided by n plus 1 plus 5. Okay, so the sequence of every sequence, the terms of the sequence are defined by 3 over n plus 5. Right, for a sequence to be decreasing, right, each next term has to be less than the previous term. So if you start with the term, the nth term, 3 over n plus 5, to be decreasing, the next term has to be smaller, right? For a sequence to be decreasing, the next term has to be smaller. The next term is just replacing n by n plus 1, right? Because if the nth term, you use n for it, the next term is the n plus first term. So you're just substituting n for n plus 1. So the n plus 1 term is 3 over n plus 1 plus 5. That's the next term. Okay, and so since it's decreasing, given any nth term, 3 over n plus 5, the next term, 3 over n plus 1 plus 5, is smaller. So 3 over n plus 5 is strictly greater than 3 over n plus 1 plus 5. Okay, so you get that inequality. Okay, and so this is equal to 3 over n plus 6. So what you have is 3 over n plus 5 is strictly greater than 3 over n plus 6. And so, so for any n greater equal to 1, 3 over n plus 5 is strictly greater than 3 over n plus 6, right? Because this denominator got larger. And so the fraction got smaller, right? 3 over n plus 5 is strictly greater than 3 over n plus 6 because the denominator is larger. Same numerator. Okay, and 3 over n plus 6 is 3 over n plus 1 plus 5. So that says that the nth term is strictly greater than the n plus first term. And so that means the sequence is decreasing. Okay, so we showed the next term is smaller than the previous term, than any previous term. Next term is smaller than the previous term. So a sub n and so so a sub n is strictly greater than a sub n plus 1 for all n greater than or equal to 1. So the sequence is decreasing. Okay. So that's that example. Next example. Show that the sequence a sub n, which is equal to n over n squared plus 1, is decreasing. Solution. Okay, so we want to show this is decreasing. So we must show that in order to be decreasing, you have that the a sub n plus 1 term is strictly less than a sub n. So now I'm just looking at it from the perspective of the n plus 1 term first. So to be decreasing, the next term has to be less than the previous term. Now we have to have that inequality. Okay. In other words, right, for any n greater than or equal to 1, you have to have that the n plus first term, so the n plus first term is replacing n with n plus 1. That's n plus 1 over n plus 1 squared plus 1. So that's the n plus 1 term. You want to show strictly less than the nth term. Okay, so we must show that the n plus 1 term is strictly less than the nth term for any n greater than or equal to 1. We need this inequality. Okay, and so Okay, so I'm going to do this on the whiteboard. Okay, so we have this inequality here. And then we can continue this quickly on the whiteboard. So n plus 1 over n plus 1 squared plus 1 is strictly less than n over n squared plus 1. That's equivalent to saying that when you cross multiply, you get n plus 1 times n squared plus 1 is strictly less than n times n plus 1 squared plus 1. Okay, so you just cross multiply. You say that this times this is strictly less than that times that. Okay. Well, that's equivalent to the thing you get on the left side, which is n cubed plus n squared plus n plus 1. That's strictly less. So n cubed plus n squared plus n plus 1 is strictly less than that whole product, which is simplifying. You get n cubed plus 2n squared plus 2n. Okay, and so then that's equivalent to just canceling terms on both sides. So you can cancel this term with this term. One of these 2n squares you can cancel with this. One of these n's you can cancel with that. And so moving them all to one side, you get this is equivalent to 1 is strictly less than n squared plus n. Okay, so n is greater than or equal to 1 by assumption, right? And so that means that n squared is greater than or equal to 1. And so then that implies that n squared plus n is greater than or equal to 1 plus 1, which is 2, which is greater than 1. So that implies that n squared plus n is strictly greater than 1 for every n. Okay? So what we have here is that since n is greater than or equal to 1, n squared is greater than or equal to 1. That means that n squared plus n is greater than or equal to 1 plus 1, which is 2, which is greater than 1. Therefore, we have this is greater than 1 for every n. So we have that n squared plus n is strictly greater than 1 for every n. So this is right. This is true. And so that means that this inequality is also true. They're equivalent. They're both true. They're both false. And so since that's true, that's also true. And we now have the n plus 1 term is strictly less than the nth term for every n. Okay, so for every n, this inequality holds. That's good. That's right. That's true. And so this inequality is also true because they're equivalent. And so going back to the whiteboard, going back to here.
Wait, Professor.
Yeah, this. Let me just write this here.
Yeah.
This inequality is proved for all n greater than or equal to 1 in the whiteboard. On the whiteboard. Okay, question? Yeah.
Yeah, can you go back to the whiteboard really quick?
Sure. There you go.
In the bottom right, the thing you circled in red, what does that say?
For every n. So I'll write it in words. For every n. Okay. For every n. Okay, so for every n. Okay, good. Okay, good. Okay, so back here. Okay, so we proved that. Another definition. The section's very long. Okay, so definition. A sequence A sub n is bounded above if there is a number, capital M, such that a sub n is at most greater or equal to capital M for all n greater or equal to 1. So a sequence is bounded above if there's a number capital M such that all the terms are, less or equal to capital M for every n greater or equal to 1. Right, so that means that every term is at most some number capital M. That's what it means to be bounded above. Okay. Okay. Definition: a sequence. Okay, a sequence a sub n is bounded below if there is a number, capital M, such that a sub n is greater or equal to capital M for all n greater or equal to 1. Okay, so just like kind of similarly to with increasing, decreasing sequences, the inequalities seem to go in the opposite direction of what you might intuitively think, right? To bound a sequence from below, use the greater than or equal symbol, right? So a sequence a sub n is bounded below if there is a number capital N such that a sub n is at most capital M for every term. I mean, a sub n is greater or equal to capital M for every n, meaning at least M. That means at least M in words. This says at least M in words. Okay, so a sequence is bounded below if there is a real number M such that all the terms are at least M. That was what it would mean to be bounded below. So those are two definitions. Okay, so another definition. A sequence is bounded if it is bounded both above and below. Okay, so sequence is bounded if it's bounded both above and below. So if you show it's bounded from above and bounded from below, it is then called bounded. Okay, so examples. So if you looked at a sub n equals to n, right? This is bounded below, right? Because it is bounded below by 0, right? All the terms are greater or equal to 0. So a sub n equals n is bounded below, but the sequence is not bounded above. So this is an example of a sequence that's bounded below, but not bounded above. Okay, and then the sequence a sub n is equal to n over n plus 1. Okay, is bounded because all the terms is between 0. All the terms a sub n are strictly between 0 and 1 for all n greater than 1. Okay, so every term of the sequence is less than 1 because the denominator is larger than the numerator, and it's positive. So all the terms are positive and strictly less than 1. So it's bounded below by 0, bounded above by 1. It's both bounded above and below, and so it's bounded. Okay, so that's another example. Okay. Good. So a fact is that not every bounded sequence is convergent. Okay, so here's an example of a of a bounded sequence that is not convergent. Your first thought might be, well, if something's bounded, it has to be convergent. But just look at the sequence we thought about earlier. A sub n equals -1 to the n is bounded, right? It's bounded below by -1 and above by 1, right? The sequence A sub n equals -1 to n is bounded, right? Well, it's bounded below by -1 and bounded above by 1, right? But the terms alternate between -1 and 1, and thus the sequence does not converge to a limit, to any limit. Right? Okay, so it's bounded, but it does not converge. So that's the example of a sequence that's bounded but does not converge. So you cannot say that because a sequence is bounded that it's convergent, right? And this is a counterexample to that statement. Okay, and so now the next thing is called the completeness axiom. For the set capital R of real numbers. Okay, it says if capital S is a non-empty set of real numbers that has an upper bound, capital M, meaning that X is less or equal to capital M for all X in capital S, then capital S has a least upper bound. Okay. Okay, so this means that B is an upper bound so this means that that if B is an upper bound for capital S, then capital M is less or equal to B. Okay. Oh wait. If S is has an upper bound M, then S is. This means that if capital M is an upper bound for S, then little b is the least upper bound of M. Okay. Then B is less or equal to capital M. All right. Okay, so if n for any upper bound of the set, there's some number B called the least upper bound, just that B is less or equal to M. It's an upper bound that's less or equal to any upper bound for the set. Okay, this is called the completeness axiom for the set R of real numbers. Completeness of the real numbers means that there's no holes in the real numbers. Okay, there's no point where you have a space where there's no numbers. The real line is full. You draw the real line. Every point on the real line is a number. You can't find anywhere in the real line where there isn't a number. That's what the completeness of the real numbers means. And it's expressed, weirdly enough, by this statement. If S is a non-empty set of real numbers that has an upper bound M, then S has a least upper bound. Okay? So let me illustrate on the whiteboard what this means. Okay? So you have your real line, right, which is complete. According to this, there are no holes in it. If you take any subset of R, let's say you take this subset, and by the subset I mean both intervals, the union of both intervals, and let's say this is 1, 3, 5, 9. Then we can talk about the least upper bound for this set. Okay, if you looked at a number like 10, 10 is an upper bound, right? 10 is an upper bound for this set because all of the numbers from 1 to 3 or 5 to 9 are less or equal to 10. 10 is an upper bound, but it's not the least upper bound. We also do 9.5. So 9.5 is also an upper bound. All the numbers in these two intervals are less or equal to 9.5. So 9.5 is also an upper bound. But is there an even smaller one? There is. You can see here, this is a smaller one and a small one. You can always find a real number. Here, you can see how there are more real numbers that are also upper bounds and smaller. So neither of these two are the least upper bound. But the real numbers satisfy this completeness axiom that says that there is a least upper bound for every set. That means that here, that least upper bound is realized by the number 9. 9 is the least upper bound of this set S, which is the union of those two intervals. It is the smallest upper bound, right? The real line has a smallest upper bound for that union of those two intervals, that subset of R, okay? And in that way, there can be no holes in the real line, right? So if there was a hole, you could approach a point, but there'd be no way to realize that point, right? Because every subset of R has a least upper bound. If you're approaching a point but through a set, you're going to have that. You're going to have that instead of a hole, there's going to be a real number there, which will be the least upper bound of that subset of R. And so there are no holes in R because of this completeness axiom. The fact that every subset of R has a least upper bound. I mean, every subset of R with at least one upper bound has the least upper bound, right? So, if you had the real line and you took all the numbers greater than 1, right? If you thought of this set here, there's no upper bound for that set, right? You're thinking of all the real numbers going to the right of some point. There's no upper bound. And so if there's no upper bound, there's no least upper bound, right? So, so you don't have to worry about that. This is no problem because the assumptions in the theorem say that your set has to have at least one upper bound. By showing 10 as an upper bound, we've shown there's at least one upper bound. And then we can talk about, the conclusion is that we can then talk about a least upper bound for that set. So one of the assumptions is there's at least one upper bound. Then the conclusion is that there's one least upper bound that's realized by a real number, okay? The fractions don't have that property, right? You can have a subset of R where the right interval is pi, right? And so if the right endpoint of an open interval is pi, the least upper bound should be pi, but pi is not a fraction. And so the fractions don't realize this. There are holes in the set of fractions, okay? So the fractions do not fill up the entire real line because it does not satisfy this completeness axiom. Okay, so that's that. And one last thing in the section is done. It's called the monotone sequence theorem. Okay, every bounded monotonic sequence is convergent. Every bounded monotonic sequence is convergent. So if you have a sequence that's bounded and it's monotonic, meaning increasing or decreasing, therefore it has to converge. Okay, and so this is the end of 8.1. So remember, 8.1 is not on the exam. The exam ends at 7.7. 7.7 is covered on the exam, but 8.1 is for the third exam. Okay, the exam is next class, right? The test, this is an important reminder, right? Test 2 is next class on April 26th, right? April 26th during class. Okay, you can use the Zoom link. You can't use the Zoom link to attend. Use the same Zoom link you use to attend every class. Okay. So the Zoom link you use to attend this class, it's the same Zoom link to attend that one. Make sure your audio and video works, right? Make sure you have Zoom downloaded on the digital device you're using to take the exam. Make sure to have at least 10 sheets of paper with you during the exam. You can make sure to read the things I said for the rules for the exam online. If you go to the menu bar and you click tests, there's then on the screen, there's 2 files, Word documents I have there, all the things you need to know before taking an exam online to help you prepare. Test to make sure your audio and video works. Okay, if you test your audio and video before the exam starts, you'll know whether or not it works during the exam, right? Also, make sure that you know how to send an email for the exams, right? Make sure you have it figured out that you know how to send your exam to me by email after the exam, right? So I told you Genius Scan is one way. You could download the app Genius Scan on your cell phone, and then you can take pictures on your cell phone using it, and then you can send the PDF file it creates in an email to me directly from your cell phone. That's one way to do it. Don't take pictures of it with your cell phone. Try not to take pictures with your cell phone. Try not to use a scanner. Those take up too much space, and then you'd have to send one picture for each page, right? So you need to find a way to do it like the way I said with Genius Scan, where it compresses the file size, so that way you can send multiple pictures in a single email. Okay, so I'll go over all this again before the exam starts, but making sure that you know about these things now. And so we had a lot to cover, so I have to go through this material. So what I'm going to do is I'm just going to stay here. So if you have questions, if you want me to go over things for the exam, I'm here, and so I'll just stay here for a while. So if you want me to stay for a half hour longer to help you with the exam, I'll do that. There's also office hour at the end of this week, and so if you have questions about the exam you want me to answer, you can attend office hour, and we'll do that. So I have to make an important change to office hours just for this week. Okay. So for just this week, office hour is still Friday, but it's from 6:15 p.m. to 7:15 p.m. Okay. So office hour for this Friday only. So for just this week, office hour is this Friday from 6:15 p.m. to 7:15 p.m. Nobody ever comes to office hour. So if you need help and you come to office hour on Friday, you may be the only person there, and you'll get as much help as you want individually. Okay. So I'm now going to stay to help you prepare for the exam. Okay. So I gave you a review sheet. So does anyone have questions about the review sheet? If you don't want to stay, you can go. If you want more help for the exam, you can stay, and I'll help you now. Class is technically over, so you don't have to stay. Also, there's office hour this Friday. So if you have to go, you can come to office hour this Friday, and I'll go over you the stuff that you missed now. Okay. So there's office hour this Friday. I'll go over anything you want, including the review sheet then. But I'm going to stay now, and I'll help you now if you need help now also. Okay, have
Professor,
a good weekend.
is the review sheet under tests?
Yeah. Wait, what?
The review sheet's under tests, and like it's over there, or where can I find it?
Well, oh, so it was just like the first exam. If you go to Blackboard and you go to the menu bar on the left and you click tests, and then you go to test 2, it's right there. So what I'm going to do is maybe I can just go to it. Okay, so I'm just going to stop sharing for a second. I'm still doing stuff. I just need to use my computer for a second. And then I'm going to sign into Blackboard for you, and then I'll walk you through it. Okay. Lots of stuff to do. Okay, so now I'm going to, everything good here? Everything's good.
I found it. Thank you.
Oh, you did find it?
Yeah, I got it.
Oh, okay. Well, you know what? I'm going to put it on the screen now because I spent this work doing it. Okay, so here's Blackboard, right? You go to tests, go to tests, and then you go down to test 2. And then you go review sheet for test 2. And it'll download it for you. What's going on? Okay, this was the review sheet, right? So it has a whole lot of problems here. Anyone have questions about certain problems they want me to go over? Anyone do the review sheet? So, anyone? So I could choose one randomly. I mean, you should study the whole review sheet. So, I'm not. This isn't a bias even towards particular problems. I don't think. I'm just randomly choosing one. So this is 6.6, number 8. I'm going to look at. Okay. So 6.6, number 8.
Professor, one more question.
Yeah.
Which review day? I mean, which class day was the review?
Sorry.
Which lesson number was the review for this test?
No, I'm saying now I'm reviewing.
Oh, the review is going to be right now for the whole test?
Yeah. I'm saying that we finished the material last class, and so we had the homework for the last material today. So the review day is today, because this is when we finished going over the homework, or we had the homework due today. So today it's now. So I just have to extend class because we have so much material. So I'm going over the review now. So if you're attending this now, you're not missing anything. I'm reviewing it now. Nobody had particular questions about the review sheet. So I'm just doing one. So 6.6, number 8, it says, determine whether the integral is convergent or divergent. So, we're going to go from 1 to infinity of 1 divided by 2x plus 1 cubed Okay, so we want to find this integral. So we want to determine whether it's convergent or divergent. So this is an indeterminate. This is an integral, indeterminate integral of improper integral of type 2, right? So this is an improper of type 2 because the interval of integration is infinite. Right, so when reviewing, this is an improper integral of type 2. Okay. Okay, have a good day. Okay, right, so I actually am still recording. That's a good point. It's going to be recorded, so people can watch that also. Okay, it's on YouTube. It'll be on YouTube. Okay, so now I'm going to take the limit as m approaches infinity of now the integral from 1 to m of that. So it's okay. So you take the limit of that, and so now that's the limit as m approaches as m approaches infinity of that integral. And when you calculate that integral, right? So you're going to use u substitution to calculate the integral. So use u substitution to calculate the integral. This guy. Oops. Okay, so we're going to use u substitution to calculate that integral. So there's the integral. And so let u equal to 2x plus 1. Okay, then du is equal to 2 dx. So we get u substitution that this integral is equal to now definite integral is equal to definite integral of so what we have here is a 2 dx, so we need a 2 dx still. So I'm not going to substitute yet. I'm just going to get ready for the substitution. So you have this 1 over, still have this. And now what I want is a 2 dx here, the substitute. So if I'm multiplying the inside by 2, I have to multiply the outside by 1/2. So now you get this equals that. So now you have 1/2 times the definite integral. Let's see, I have definite integral. So now this is the same as 1 over u cubed. because the denominator is u and you're cubing it. 2dx is du. And then, and so now if x is 1, u is 2 times 1 plus 1, which is 3. And if x is m, this is 2m plus 1. Okay, so now you have that. And then so this is equal to the def integral. I'm just going to write this in exponential form. So 2m plus 1 over time u to the -3 du. And so now this is equal to 1/2 times u to -3, an antiderivative of that is u to -2 over 2. So this is the same as u to the -2 divided by -2. Because you add 1 to the exponent, divide by it. This is evaluated from 3 to 2m plus 1. And so now this is equal to 1/2 times this minus that, where this is plugging in 2m plus 1. So I'm going to actually move the -2 out in the denominator. So it's going to be -1/2 there for that -2. And then I'm going to evaluate u -2 from 3 to 2m plus 1. So this is going to be 2m plus 1 raised to the -2 power minus 3 raised to the -2 power. There's a 2 here. Okay. And so you get this. Okay, so you get this thing. And so this thing is the value of that def integral. So this is -1/4 times what's in this bracket here, which is this minus that. Okay, so this def integral is equal to this. Okay, and so going back here, when you want to find the limit of that def integral, you're finding the limit of this expression, which is the value of that def integral. So you want to find the limit of that. And so now this is equal to the limit of this guy. Well, you have the -1/4 here. Okay, but now in the bracket, you calculate this limit of this minus this. This is to -2, so this is 1 over 2m plus 1 squared. This whole thing goes to 0, and you're left with -1 to -9. You get -1/9. Got the equal sign. So it's -1/4 times -1/9, and so then that's equal to 1 over 36, and that's the answer. Okay. Okay, so that improper integral is equal to 1 over 36. Okay, and so that's number 8. Okay. So are there other problems from the review sheet? So we have this review sheet here. Right, and so I went over 6.6, number 8. Okay. Just no particular questions, then I can just randomly choose one again. Okay, there's still people here. Okay, good. Okay, so then okay, so it's on the whiteboard. It's a chat. 6.6, number 44. Okay, 6.6. Oops. This for a second. 6.6. Wait, did you say 6.6, number 44?
Yeah, it's a homework.
Oh, okay. 6.6, 44.
Thank you.
You're welcome. Okay, so we have 6.6, number 44. So use the comparison theorem to determine whether the integral is convergent or divergent. Okay, so what we have is the integral from 0 to infinity. From 0 to infinity of arc tan x divided by 2 plus e to the x dx. Okay, and so you want to use the comparison theorem to determine the integral is convergent or divergent, right? Okay, so right, so if you look in the book, if you have the book in front of you, it's page 365 that tells you the comparison theorem, right? So on page 365 or the class notes is the definition of the comparison theorem. Okay, so what we want is we want to somehow sandwich. If we want to show, it depends whether or not we want to show this convergent or divergent, right? So if we want to show that the integral is convergent, then we need to think of a function. We want to think of a function that's sandwiched between 0 and some other function, right? If we want to show it's divergent, we want to somehow show it's that the values are larger than some given function. Okay, so the first thing I think of arctan is that this is sandwiched between something. I'll show you why. So for arctan of x, here's the x-axis, here's the y-axis, right? For arctan of x, the graph of arctan of x looks like this. Okay, so this is y equals arctan x. It's inverse of tan x, right? This is the graph of it. Then it has, as a horizontal asymptote, it has y equals pi over 2 and y equals negative pi over 2. Those are the two horizontal asymptotes. And so since all the values of arctan of x are between these two, then my first thought is let me sandwich the values between negative pi over 2 and pi over 2. Okay? So from the whiteboard it is illustrated that that negative pi over 2 is less or equal to arctan x, less or equal to pi over 2 for all x, for all real numbers x. Right? So you have arctan x between those two values. Okay. Now, okay. So okay, so let's look at the absolute value of arctan x. Okay, so let's look at the absolute value of arctan x divided by 2 plus e to the x. Okay, well, this is less or equal to, so the numerator is less or equal to pi over 2, right? The absolute, if arctan x is sandwiched between negative pi over 2 and pi over 2, and that means 0 is less or equal to arctan x less or equal to pi over 2 for every x for all real numbers x, right? Not, I mean absolute value here. Okay, so the absolute value of arctan x is between 0 and pi over 2 for all real numbers x, right? And so that means that now 0 is less or equal to that, which is less or equal to, well, this is pi over 2 here, which is pi over 2 here in the numerator. And the denominator, I'm just going to keep 2 plus e to the x. Okay, and this is equal to pi over 2 times, well, 1 over 2 plus e to the x, right, is non-negative, so its absolute value is itself, right? This is all positive, and so this is, get rid of the absolute value sign here. So the absolute value of arctan x over 2 plus e to the x is less than or equal to that amount. Okay, so if you integrate, so then if you look at this thing, it's less than or equal to pi over 2 times, well, if you want an upper bound for this fraction, then the smaller the denominator is, the larger the fraction. And so in order for 2 plus e to the x, the denominator, to be as small as possible to make the fraction as large as possible, you want e to the x to be as small as possible, because 2 is a constant, it doesn't change. So so 2 to the x can get smaller and smaller to 0, but 0 is a lower bound for e to the x. So this is less than or equal to 1 divided by 2 plus 0, right? E to the x is always larger than 0. And so that means that 0 being smaller than any of these values, 2 plus 0 would be smaller than 2 plus e to the x. And so since 2 plus 0 is smaller than 2 plus e to the x, in the denominator, it makes the fraction larger. So this fraction is less or equal to that fraction. And so now this is equal to pi over 4. So the absolute value of arctan x over 2 plus e to the x is between 0 and pi over 4 for every x. No, wait. Okay, sorry, I have to fix this. I'm just gonna. I think I got it though. Wait, so I'm gonna have to restart this thought. Okay, so if you look at this graph, right? If you look at the height of where the height of 1 is in this graph, right? That would be a value of x such that tan x equals 1. Okay, tan x equals 1 when x is pi over 4. Okay, tan of pi over 4 is 1. And so at this point, the graph of arctan reaches a value of 1 at x equals pi over 4. And then every point after that, the height is at least as large as that, but larger, right? So that means that the integral, the area underneath this curve, is less than or equal to the area underneath the graph of arctan x, right? And so the integral that we're going to compute is calculating this red area. I mean, it's calculating this whole red area here, right? But what I'm going to do is this. I'm going to find that this red area is infinite by comparing it to this blue area. Because this blue area is infinite, this red area is infinite, which means that when you add in this, it's still infinite, okay? So so the integral you want to find, the integral from Let's see, the integral is from 0 to infinity, right, of arctan. So we want the red area and the area of the red plus the area of the green to find that integral. And so if I find the area of the red region is infinite, then the area of the red and green region is infinite. And so the way to show that the area of the red region is infinite is by comparing it to the area of the blue region. Blue region exists entirely inside the red region. So if the blue region takes up an infinite amount of space, then the red one also does because it's larger. That's the comparison theorem for integrals. Okay? That this integral we're going to compute is going to compute an infinite area, which is at least the red area. And since the red area is infinite, then the red and green regions together is infinite. Okay, so let's do that. Okay, this graph is f of x equals 1. This blue line. And the other one is f of x equals arctan x. So for every x greater than or equal to pi over 4, 0 is less than or equal to f of x is 0 less or equal to f of x less or equal to that. Oh, actually, okay. So to relate it with the comparison theorem, I would call this g of x then. So it matches with the theorem. G of x equals 1 will match with the comparison theorem. Part B. Okay, so we're going to use the comparison theorem part B. Okay, so we are going to use the comparison theorem part B. Okay, and so to do that, we're going to consider the fact that 0 is going to be less than or equal to g of x, less than or equal to f of x. And this is going to be for all, oh, it says for all x greater than a, right? So for all x greater or equal to pi over 4. Okay, so we're going to use a comparison theorem part B. And so this is what we want. And so we're going to define g of x equals to 1 for all x greater or equal to pi over 4.
Sorry, Professor, it's still on a whiteboard.
Oh, okay, thanks. Okay, so here we are. Okay, so now you should be able to see it. So g of x is 1. So f of x is greater or equal to 1 for all x greater or equal to pi over 4, like I illustrated in the picture. And so we have this inequality here. And so by the comparison theorem, part B, on page 365 of the textbook, or in the notes, right? We have that if the definite integral from a here is pi over 4, so if the improper integral from pi over 4 to infinity of g of x dx, which is 1, of 1 dx is divergent, then the integral from pi over 4 to infinity of f of x dx. And so f of x is this. Is divergent, right? So we're going to define, well, I'm just going to state this. F of x is that function there in the integrand, right? And this is for all x greater or equal to 0. Okay, so I'm including 0 here. Okay, so 0, I'm including x greater or equal to 0 here. Okay, so because here 0 to infinity. Okay, so if we show this is divergent, then that's also divergent by the comparison theorem. Well, if we take this integral, this is equal to the limit as m approaches infinity of the definite integral from pi over 4 to m of 1 dx, right? And that's equal to the limit as m approaches infinity of that definite integral, which is x evaluated from pi over 4, x evaluated from pi over 4 to m. But that's just the limit. It's just the limit as m approaches infinity of capital M minus pi over 4. Okay, but that's infinity, right? Because it's infinity minus pi over 4, that's infinity. Okay? Okay, so that tells us that this integral is divergent. Its limit is infinity. We would need a finite number, right? So that is divergent. So this is divergent, right? From that statement above. So now we have that this is divergent. Okay, but let's also realize this, that now we can use the comparison theorem again. Actually, no, never mind. Not the comparison theorem again. Let's make, I'll make the observation this way. If you take the integral from 0 to infinity, right? If you take the integral from 0 to infinity, this is equal to the integral from 0 to pi over 4, which is positive, plus the integral from pi over 4 to infinity. Okay, well, this is equal to a positive number plus infinity, because this is infinity. We showed that this, this is divergent. We showed this is infinity, right? Divergent to infinity. Okay, because it's at least this integral. Okay, because the f of x function is greater or equal to this function, and so if this thing is a positive infinity, then this thing takes up more space, and this is also infinity. So this integral is a positive number plus infinity. And well, a positive number plus infinity is infinity, and so this integral is also infinite. And so the original integral diverges by the comparison theorem. Okay, and then the problem is done.
Okay, thank you. So
That makes some sense?
yes. So if the smaller one we find that is convergent, can we say that the bigger one is convergent?
You mean, wait, this one?
No.
This one?
Yeah. If the smaller one we find is convergent, can we say that the bigger one is convergent, or?
Right, so if this one was convergent, right, then that would mean, since this is also convergent, then you'd get a number plus a number would be a number, and then this would also be convergent. Yes, if this was convergent, then that would be convergent.
Okay, thank you. I got it.
That makes sense? the way to illustrate it, because before you do all this math, and it actually makes it easier. It's easier if you can kind of see ahead where you're going. And so this integral, that integral I was just saying, is this green area, right? If you're integrating from 0 to pi over 4 of arctan x, you're finding the finite area underneath this curve from 0 to pi over 4. See that?
Yeah.
Right?
Okay.
That depth integral represents this finite area. And so you'd have to get a finite number. So when you calculate it, you would get a finite number. And so by looking quickly at the graph, you see where, before you do all the work, you'd see what you'd get, right?
Okay, thank you.
Okay, you're welcome. Other questions about the review sheet or anything else pertaining to the exam? Not many people left, so how many people? There's 2 people left. Okay, so there were all these questions. Any other questions about the review sheet? Okay, so I guess I'm gonna stop because I don't know, there's no one else here. So, and no more questions. Do you guys want me to do another problem in the review sheet randomly or something?
No.
No? Okay. All right. So if you want me to stop, I'll stop. I'm just gonna save the whiteboard. Okay. And okay, so I'll stop here. And okay, have a good weekend, and I'll see you on Monday.
Okay, thank you. Bye.
Bye.
Bye. Have a good week.